So in the previous video, we found a range of plausible values for the parameter by testing a bunch of parameter values individually and deciding whether each one was plausible. So I don't think I need to tell you why that's not really a sustainable path forward. It's extremely tedious. So now we're going to come up with another approach. Our book calls this the 2SD approach. I think that's a little bit confusing. I'm going to call it 2SE. Because what we're really going to take advantage of here is the standard error. So we're looking at the same example again. We want to use the sample proportion, which was 59%, to estimate the unknown parameter pi, the true proportion of American adults who believe the federal government is responsible for providing healthcare coverage. So how close to the true parameter do we expect that statistic to be? And like it often is in statistics, the answer, it depends. And specifically here, it depends on the sample size, right? So how precise our estimate is depends on the sample size, because as the sample size gets larger, the standard error gets smaller, right? And the smaller the standard error, the closer we expect the statistic and the parameter to be to each other. So a better question really might be, how close do we expect them to be in terms of the standard error? So it turns out there's a helpful rule here if we're working with a normal distribution. So for a normal distribution, there's something called the empirical rule. And the empirical rule is sometimes also called the 68, 95, 99.7 rule, which is kind of a mouthful. Basically, all it says is that if you have a normal distribution, that you would expect 68% of your data to fall within one standard deviation of the mean. 95% of the data would fall within 2 standard deviations of the mean, and 99.7% of your data would fall within 3 standard deviations of the mean. So it's just giving us a general sense of how things are distributed. So what we're looking at here, this is the distribution of sample proportions. So this is the distribution of p hat values when we know the parameter. So here it's when the parameter is equal to 0.5. So this is a sampling distribution of p hat, and we know from the central limit theorem that as long as the validity conditions are met, that this distribution is approximately normal. So we can see that just by looking at the simulated null distribution. The validity conditions depend on the sample size. Our sample size here was over 2,000, and so it's definitely big enough for us to use the normal approximation. So we're going to take advantage of the empirical rule here. So remember, we're looking at a distribution of statistics. The center of this distribution is the true parameter. In this case, we were assuming that the parameter was 0.5. And this standard deviation that's here, this is the standard deviation of a statistic, which is also known as the standard error. So based on the empirical rule, we can say that the statistic falls within one standard error of the true parameter in about 68% of samples. So if we go out one standard error from the center here, we should get about 68% of our p hat values, our sample proportions. If we go out 2 standard errors, then we should be able to capture about 95% of our sample portions. And if we go out 3 standard errors, in that case, we should be able to get about 99.7% of our sample proportions. So we're looking at this situation where we know the parameter, right? We're assuming that the parameter is 0.5, and we're looking to see which values of the statistic occur. So when we know the parameter, we can say that the statistic, p hat, will be less than 2 standard errors, from the parameter in 95% of samples. So at first that seems like a silly thing to do. We're pretending that we know the parameter, but that's not actually what we have. What we actually have is a statistic, 0.59. But the reason that this is useful is because we can turn it around. If the statistic is less than 2 standard errors from the parameter, we can turn it around and say that the parameter is less than 2 standard errors from the statistic. So in this case, when we know the statistic, we can say that the parameter will be less than 2 standard errors from the statistic, just turning around our previous statement. again in 95% of samples. So in our real world scenario, where all we have is a statistic, we can use this theory to say, okay, all I have is a statistic, but I don't think my parameter is more than 2 standard errors out from this estimate. So that's the justification for the 2SE method. We can construct a 95% confidence interval of plausible values for the parameter by including all values that fall within 2 standard errors of the sample statistic. So we start with our sample statistic, which is p hat in this case, plus or minus 2 times the standard error, and that's going to give us our confidence interval. So how do we calculate the standard error? We have 2 options. One is that we can do a simulation. We can simulate a null distribution and find the standard deviation. The standard deviation of that null distribution is the standard error. So that's kind of what's going on up here, right? We've got the standard deviation of a null distribution. That's a way to estimate the standard error. Or we can plug into this formula, right? We've seen this formula before for the standard error of p hat. The problem is that both of these require you to know what pi is, right? Because if you're going to do your simulation, you have to start by putting in a value for the probability. Or if you're going to plug into this formula, you have to plug in pi, which wasn't really a problem in previous chapters because we had a null hypothesis value. And we were going through the whole process assuming that the null hypothesis was true. But now we don't have a null hypothesis that we're assuming to be true, and we don't know what pi is. So really we only have one good option, which is just to use our best estimate at this point, our best estimate of pi. And right now, the best estimate of pi that we have is our sample proportion p hat. So in this case, our sample proportion is 0.59. All right, so let's plug into this formula. I'm going to do p hat plus or minus 2 standard errors. So I'm going to do p hat plus or minus 2, and then I'm doing the standard error formula, but I'm replacing the pi with p hat because that's my best estimate right now. And then I'm just going to plug in 0.59 everywhere that I have pi. 0.59 and 1 minus 0.59, that's the proportion of failures instead of successes. And my sample size was 2004. Oops, I almost forgot the 2. Don't do that. I don't usually show you while I'm doing the calculations, but maybe I should because this is my favorite calculator. I just use the Desmos Scientific Calculator. And the reason that I really like this one is because instead of having it be all about parentheses, it actually shows it like a regular equation. So I'm going to do 0.59 plus the square root, and then inside I'll do 0.59 times 1 minus 0.59 divided by 2004. So to me, this is really a lot easier to read. Oh my gosh, I almost did it again. Don't forget your 2. Okay, so there's the upper boundary of my confidence interval, 0.612. And then I'm just going to go back and change this to a minus sign. And that'll give me my bottom boundary, 0.568. So 0.568 up to 0.612. And you can see this is very similar to the value we got before. So the general process here is that we're starting with a sample statistic. So p hat here is our estimate of the parameter, our estimate of pi. And then we give ourselves a little bit of wiggle room by adding and subtracting 2 standard errors on each side. And then at the end, we've got this range of values. And this is the range of plausible values for pi. So we think that our population parameter is somewhere between 0.568 and 0.612.